Let us solve the third numerical on vapor power cycle. I'll just read this numerical. A turbine is supplied with steam at a pressure of 32 bar and at a temperature of 410 degrees Celsius. The steam then expands isentropically to a pressure of 0.8 bar, 0.08 bar. Find the dryness fraction at the end of expansion and thermal efficiency of the cycle. If the steam is reheated at 5.5 bar to a temperature of 410 degrees Celsius, then expanded isentropically to a pressure of 0.08 bar, what will be the dryness fraction and thermal efficiency of the cycle? Now, if you see this numerical, the first part, there is an expansion from 32 bar to 0.08 bar directly. That is one part, and you are asked to find out the dryness fraction and thermal efficiency. The second part is that if it is reheated in between, like from a pressure of 32 bar, if it is expanded up to 5.5 bar and then again it is reheated to a temperature of 400 degrees Celsius, then after reheating and expansion, then it is expanded isentropically and then to a pressure of 0.0 bar. So what will be the dryness fraction and thermal efficiency? Now there are two cases here. First case and the second case. First case without reheating, second case with reheating. We have to calculate these two parameters, fraction and thermal efficiency of the cycle. The first part, if you refer this diagram case 1, you can see that at this condition at 1, which is at 410 degrees Celsius and 32 bar pressure, it is superheated steam. The condition is superheated steam. If you refer the saturation temperature for 32 bar, so it is 237.4 degrees Celsius. So it is less than this. That means this condition at 410 is obviously superheated steam. This expands in the turbine. This expands in the turbine to a pressure of 0.08 bar. Isentropic expansion, vertically downward with this pressure. Then it enters into the condenser from 2 to 3. It is completely condensed at constant pressure to the saturated liquid. Then 3 to 4 is a pump work, and 4 to 1. At 4 it enters into the boiler and heat is added from 4 till 1 at this pressure only. So from 3 to 4, for a pressure of P2, it is pumped to a pressure of 32 bar. So what would be the pump work? Pump work would be the difference in the pressure multiplied by the specific volume of this. Thus, this is the first case of the cycle. So here we need to find out what is the dryness fraction at this point and what would be the efficiency of the Rankine cycle. So let us solve this. Okay. So by a step-by-step procedure wherein you have to find out the enthalpies at all these points. Enthalpy at 1, 2, 3, 4. So if you find the enthalpies, then you can determine the efficiency very easily. So now let us go in that process. Now case 1, in this case 1, so let us find out what is the enthalpy at H1. Enthalpy at H1. So it is a superheated steam. You will have to refer the enthalpy of superheated steam table for this. Now for 32 bar, enthalpy of superheated steam table, 32 bar, at 400 degrees Celsius, you have this value. At 500 degrees Celsius, you have this value for 32 bar, but you do not have a value for 410 degrees Celsius. For that, what you'll have to do is, you have to go for interpolation, and for 410 degrees Celsius, you'll have to find this value of H1, 3252 kilojoules per kg. So this is the value of the enthalpy at 32 bar and 410 degrees Celsius. Or the other way is you can refer the HS diagram, Mollier diagram, enthalpy entropy diagram, and find out this value. That is the second case. Third case is that you can find out this value by another method, like you have to use this Hg plus CPS into T sup minus TS. So heat of superheat, you'll have to find out, add that value to Hg, again you'll get this value. So there are three ways in which you can find out this value of H1. So now, by any one of these methods can be adopted to find this value of enthalpy. Once you determine this value of H1, then how do you find the value of H2? Now 1 to 2 is an isentropic expansion in the turbine. So that means it is S1 is equals to S2. That I have expected. So entropy of superheated steam. So how do you find this value of S1? S1 can be found out from the entropy of superheated steam table. So corresponding to 32 bar, you have value for 400 and 500, but do not have the value for 410. You have to go for interpolation and find out this value. So this is S1. This is equated to S2. S2 is equals to SF2, which is for the wet steam. It is SF2 plus X2 into SFG2. So SF2 and SFG2 values can be found out from the steam table for a pressure of 0.08 bar. So these are the two values. Substitute these values, equate it to 6.922. So you will get this value of X or X2, whatever. X. Here I have represented the X2. So let it be X2. So X2 is 0.83. 0.83 dryness fraction. Once you determine this dryness fraction, then the enthalpy of wet steam is calculated as HF2 plus X2 HFG2. So again, these two values are at this pressure from the steam table. Find out these values and substitute here for this, and H2 comes out to be 2168.5 kilojoules per kg. Thus, you can find the value of H2. Now, let us find the value of H3. So, H3 stands for enthalpy of the saturated liquid, which stands for HF value at this pressure 0.08 bar. HF value you can refer from the steam table. Its value is 173.9 kilojoules per kg HF value. So that is the value of H3. So once you determine this value of H3, how do you find this value of H4? H4 is determined as usual. WP is equals to VF3 into P1 minus P2. So VF stands for the specific volume at a pressure of 0.08 bar. So referring to the steam table, its value is 0.001008 meter cube per kg. Then difference in this pressure 32 minus 0.08 into 10 to the power 5, because this is in bar, converted into Newton per meter square, divided by 1000 so that it can be converted into kilojoules. So then that value comes out to be, the work, pump work comes out to be, this is WP, comes out to be 3.22 kilojoules per kg. This is also equal to difference in the enthalpies H4 minus H2. H4 minus H3 is determined already, and only H4 find out the value of H4 from this, which will be 17.12 per kg. So once you determine all these, then you can find out W net and Q1. So efficiency is given by W net. The work of expansion minus pump work minus the pump work, which is WT is H1 minus H2. What is this pump work we have also, which is 3.2. So H2 minus, so W net comes out to be 1080 kilojoules per kg, and Q1 comes out to be H1 minus H4. So heat is added right from 4 to 1. So H1 minus H4. So these values 3252 minus 177.12. So you will get this as 3074.88 kilojoules per kg. So thus you compute these values of W net and Q1. So efficiency is given by, it's the ratio of W net by heat supplied into the. Substitute these values, its efficiency comes out to be 35.13%. So thus you have computed the dryness fraction and the efficiency. The most important thing is how do you compute these values based on the condition of steam. Like if it is for a superheated steam, if it is for a wet steam, how do you find the values? So that's all. So thus you can find out these values. Okay. So this is the first part of numerical.